Namaste dosto. Today, we're diving into the fascinating world of circles, starting with something simple yet very powerful, equal chords. Imagine slicing a circular pizza into pieces. The straight edges of your slices are like chords of the circle. Now, equal chords are those chords that have exactly the same length. Geometrically, if you take two chords, say AB and CD, inside the same circle with radius r, we say they are equal chords if the length of AB is equal to the length of CD. Because they are equal, they also subtend equal angles at the center of the circle. In other words, they lie on arcs of equal length. Interestingly, these equal chords sit symmetrically around the circle's center. So, if you drop perpendicular lines from the center to each chord, those perpendiculars will also be equal in length, meaning the chords are equidistant from the center. Another key point: the perpendicular drawn from the center to any chord always bisects that chord and gives the shortest distance from the center to the chord. Picture a circle with two equal chords, AB and CD, and from the center O, two perpendiculars, OM and ON, falling on these chords, splitting them exactly in half. Keep that visual in mind. It's the foundation of everything we'll learn next. Let's build on that foundation with a very important theorem. It says, if two chords of a circle are equal in length, then they are equidistant from the center of the circle. In simple terms, if AB equals CD, then the perpendicular distances from the center OM and ON will also be equal. And here's the fun part: the theorem also has a converse. If two chords are equidistant from the center, then the chords are equal in length. So if OM equals ON, that means AB equals CD. This gives us a beautiful way to check for chord equality by just measuring their distances from the center. Picture again, chords AB and CD, both in the same circle, with perpendiculars OM and ON drawn from the center O. We'll now prove why this property is always true. Let's get mathematical with the proof. We are given two chords AB and CD in a circle, such that AB equals CD. From the center O, we draw perpendiculars OM to AB and ON to CD. Now focus on the two right-angled triangles, triangle OMA and triangle ONC. We know OE equals OC because both are radii of the same circle. AB equals CD, that's given. And both OM and ON are perpendicular to the chords. So, by the right angle hypotenuse side congruence rule, or RHS rule, we can say that triangle OMA is congruent to triangle ONC. By congruence, their corresponding sides are equal. So OM equals ON, that's exactly what we wanted to prove. Equal chords are equidistant from the center. Mathematically, we can write AB equals CD implies OM equals ON. Now, let's flip the situation and prove the converse of that theorem. Suppose two chords AB and CD have perpendicular distances OM and ON from the center, and these distances are equal. That is, OM equals ON. We'll again look at the same two triangles, triangle OMA and triangle ONC. We already know that OE equals OC, since both are radii of the circle, and OM equals ON by given information. Each triangle also has a right angle where the perpendicular meets the chord. So, by the RHS congruence rule once again, triangle OMA is congruent to triangle ONC. By the property of congruent triangles, the corresponding paths are equal. That is, AM equals CN. Now remember, the perpendicular from the center always bisects the chord. So AB equals 2 times AM and CD equals 2 times CN. Since AM equals CN, that means AB equals CD. Hence proved, if two chords are equidistant from the center, they must be equal in length. Let's apply this theorem with a simple example. In a circle of radius 10 centimeters, two chords AB and CD are each 12 centimeters long. We need to find how far each chord lies from the center O. Half of each chord is 6 centimeters, so let's call that AM equals 6. We'll use the right triangle OMA, where OA equals 10, AM equals 6, and we need OM now by the Pythagoras theorem. OM squared plus AM squared equals OA squared. Substitute the values. OM squared plus 6 squared equals 10 squared. That means OM squared plus 36 equals 100. Simplifying, OM squared equals 64. Taking square root on both sides, OM equals 8 centimeters. Therefore, both chords are at a distance of 8 centimeters from the center. Perfectly fitting our theorem, equal chords lie at equal distances from the center. Now, you might be wondering, where does this apply in real life? Well, this geometry isn't just theory. It's seen in the real world all around us. Think about wheels, clock dials, and circular machine parts. If two bolts or notches are placed at equal distances from the center and they form equal chords, then the design is perfectly symmetric. This helps engineers, designers, and architects ensure balance and accuracy. For example, if 2 points on a wheel rim are equidistant from the center, then the arc or sector between them will be identical on both sides, making cutting, wiring, or layout far simpler. Conversely, by measuring perpendicular distances from the center, you can check if two features are symmetrical, even without measuring the chords directly. This makes the theorem a practical tool in design, construction, and even robotics, where precision and symmetry matter most. Alright, let's wrap it all up with a quick summary. First, equal chords of a circle are equidistant from the center. That means, if AB equals CD, then OM equals ON. Second, the perpendicular from the center to any chord always bisects that chord, and this fact is the backbone of our proof. Third, the converse is also true. If OM equals ON, then AB equals CD. And a key geometric idea behind both proofs? The RHS triangle congruence rule, right angle, hypotenuse, and side. Finally, remember the practical insight. These theorems explain symmetry and balance in circular shapes, from wheels to watches to engineering designs. So next time you see a circular dial, a steering wheel, or even your favorite pizza, you'll know equal chords and equal distances make the magic of perfect geometry happen. Shabash, dosto. You've mastered one more powerful concept in the geometry of circles. Keep practicing, keep exploring, and I'll see you in the next session. Happy learning!